So it's my pleasure today to welcome Professor Richard Zare, who is a distinguished professor in natural sciences at Stanford University with appointment in the Department of Chemistry and a courtesy appointment in the Department of Physics. He graduated from Harvard University, where he received a BA degree in chemistry and physics in 1961 and his PhD in chemical physics in 1964. In 1965, he became an assistant professor at MIT, but moved to JILA, University of Colorado Boulder in 1966, remaining there until 1969, while holding joint appointments in the Department of Chemistry and the Department of Physics and Astrophysics. In 1969, he was appointed to full professorship at the Department of Chemistry at Columbia University, becoming the Higgins Professor of Natural Sciences in 1975. In 1977, he moved to Stanford University. He served for 6 years as the chair of the Stanford Chemistry Department. Professor Zare is renowned for his research in lasers applied to chemical reactions and chemical analysis. He is the recipient of many awards, including the National Medal of Science in 1983, the Welsh Award in Chemistry in 1999, the Wolf Prize in 2000. These are only a couple of the awards, so again, like usual, we can go on for days. All right, then I'll kill off with this. He's authored and co-authored over 1,000 publications and has nearly 100 patents. So without further ado, thank you, Professor Zare.
Thank you so much. Does this work?
Yeah, oh, for sure you can use.
I'll just use this?
Yeah.
Okay. You can hear me, I hope, in the back? Great, thank you so much. I am so grateful to Pat for inviting me here and giving me this opportunity to tell you about water. Your first reaction may be, well, come on, water's been studied for so long, there's nothing much more to learn about it. But not so. We're still learning things about it, because I'm going to try to convince you. And so the title of my talk is The Wonders of Water Droplets in Air Bubbles in Water. I'm very much interested in interfacial chemistry. And I want to show you it's quite different than what you may have heard of before. Anybody, let's see if this works. Anybody who wants a copy of this presentation, here's my email address. Just email me and I'll send you a copy. Probably the presentation is too long, so I have to send you a link that you download so you understand what's going on. Let's begin. Okay? The key finding. Whereas bulk water is inert and benign, water droplets in air, or air bubbles in water, have a highly reactive interface. This is what's going to be different. Okay? And so what makes this interface so special? And this is really true whether it's water with gases, water with liquids like oil that don't dissolve in water, or water with solids, like all particulates that you can find. So that'll mean like aerosols, or for that matter, different surfaces. But they need to be, as you'll see, water droplets. There needs to be curvature, and I'll get to that. Let's begin. And I gather some people up here, maybe from 8th grade or something like that. Am I right in what I'm saying?
Yep.
Yeah. Okay, look, good. So look, suppose I ask someone in 8th grade to tell me what's in a 1 liter beaker of pure water, assuming you've had some chemistry. I hope so. And the person will say to me, well, I know the answer to that. Okay, you know, 1 liter is 1,000 milliliters. It's 1 gram per milliliter, so that weighs 1,000 grams. And water is H2O. That's 16 plus 2 is 18. So I divide 18 into 1,000, and I know the answer. This is 55 moles of H2O. HOH, bent. And I smile and I say, yes, that's right. What else is there? And often a student will look at me and ask, are you talking about isotopes, like deuterium and hydrogen? I said, no, I understand isotopes. I want to know what else is in this beaker. And the student will say, actually, we learn often in beginning chemistry that there's 10 to the minus 7 moles of H+, which we call the hydronium ion, and 10 to the minus 7 moles of OH-, which we call the hydroxide ion. And that's why everyone who starts chemistry learned that the negative logarithm to the base 10 of the H plus concentration is pH, and the pH of neutral water is room temperature, 1 atmosphere pressure, 7, right? So we understand this is all so. And I say, great. Now, have you ever thought about what is the pH of a water droplet in air at the surface? And the person looks at you, and you're a professor of chemistry, so probably the answer isn't 7, but what is it? They don't teach this at all, right? And so now things become interesting. We're going to go on. And I want to show you something. This is something called DFT, density functional theory calculations. And we're going to look at the H plus and the OH minus, okay, in bulk solution. And the question is, do they ever form OH and H? After all, in the gas phase, if you were to bring a proton with an OH minus close together, electron would jump. You get H and OH. But this is now in water. They're fully solvated in 3 dimensions. No way does this happen. You make the calculation, trust me, because we have, and you find that it is endothermic, takes energy of 97.6 kcals per mole. Okay, so right, if it did, after all, if this were happening in bulk water, it should be bubbling out hydrogen. It doesn't do that. You all know that, right? Now, what you probably don't know, and it'll come, I think, as a surprise to many, is that for liquid water at the air-water interface, which I'm going to use an S for surface, the process is actually exothermic. Exothermic, meaning it goes, and it's minus 88 kcals per mole. And so it's making H and OH. That's the hydrogen atom, right? And the hydroxyl radical. Some of you know that the hydroxyl radical is what cleans up the atmosphere. Highly reactive. So is the H atom. Okay? So, and I'm saying to you that that's so. Your first reaction, because they don't teach this in general. I'm telling you, they don't even teach it at Stanford, where I am to undergrads. But this is really what happens. How do I know this is so? I'm going to show you. Here's a student of mine who's now returned to China, where he's an assistant professor at Wuhan, China, and he used, in Professor Ed Solomon's laboratory, the electron spin resonance machine, ESR, and he used this compound called DMPO, D-M-P-O. You can see what it is from the slide, right? And he's able to capture this, radicals, free radicals, and he finds, and they're shown right here, that there is H, and there's OH from water droplets. And moreover, when O2 is around, you get O2 minus. Highly reactive. Wow. Huh? Wow. That's not what they generally tell you. But it's so. And that's going to be key to understanding the rest of this talk. Okay? And you initially may say, I don't believe it, but I'm showing you. Look, we have evidence of it. And I'll show you yet more evidence of it. Now that I have that the water droplet is highly reactive, bulk water is not, we're going to start to see things happen. And one of the things that happen is that the OH radical and the other OH radical find each other, and you get what's called recombination. 2 radicals recombine, and they make HOOH, or H2O2. You'll recognize that as hydrogen peroxide. Okay? And I'm telling you that water droplets, like rain, have hydrogen peroxide in them. Okay? Really so. Now, people first saw that there was some hydrogen peroxide, and they said, oh, it must be coming from the upper atmosphere in some way, from ozone. No, ozone can also make this, but no, this is just happening without ozone. Truly so. And to prove this, let's now take this compound. This compound was made at UC Berkeley by these people, and it's a compound that has an IUPAC name, forget it. I'm going to call it PF1. IUPAC name does not help you, but you'll see it has a carbon-boron bond, and that is broken by hydrogen peroxide, and when you break it, you form this molecule, and some of you will recognize this molecule as what's called fluorescine. And it is fluorescent. Okay, when you shine light on it, it will glow. This does not. This is non-fluorescent. Well, let's look at this. We're going to take this compound and we're going to add it to water. And let me show you now some pictures of this. I hope you can all see this. So we have to tell the lights, maybe killing the lights in front may help. I'm not sure. Devin, if you can help.
There's skylights here.
You're just going to stay the way they are. Okay. Okay. Well, it turns out here's the bright field of the water, bulk water. Here's this fluorescence. I see nothing. I don't know about the rest of you. Here is air-water interface, flat. I see nothing. Right? Now, let me put in some bubbles. Wow. Huh? And moreover, the little bubble, pretty bright. Indeed, we can look at this, and I want to get this across to you. This is a study we've made. Look when it's published. It's published in, what year? Come on, 2019. That's a while ago. Okay. And done by these people in my lab. And we're looking at A, B, and C. What's A? A is 160 microns across. I'll remind you, a human hair is about 100 microns in diameter. B is 50 microns, half a human hair. And C is 16 microns. And wow, C is really lights up. B, there's some green there. And those in the front row can maybe see that A still has something, but it's almost gone. And this plot on the right shows you that the smaller droplets really have this, and that's why it's been missed, because it wasn't first looked at that easily that way. I was so excited about this that I decided that this thing going to change the way people look at things, so I sent it off to Nature to be published. And a woman, I'll remember, editor Magdalena Helmer, sent it out for review. And interesting, it got back two types of reviews. One reviewer said this is unbelievably exciting. The other reviewer said this is unbelievable. And so Magdalena called me up and she says, Dick, she says, people have been looking at aerosols, small droplets, for years and years. If this were true, it would have been seen already. That's not a scientific argument, and I knew no way to defeat it. So it was published in PNAS, okay, another journal. But it's so, okay? And now what's going on? So I worked with Professor Wei Min at Columbia University. This is my student J.K. Lee there from Korea, who's back now at Seoul National Laboratory, National University, pardon me, SNU, in Seoul, Korea. Anyways, they measured in a water droplet next to oil, they saw a stark shift. How big a stark shift? 5 wave numbers. Okay, that's a big thing in spectroscopy. And you work it out, and it corresponds to an electric field of 10 to the 7th volts per centimeter. Hopefully some of you have an idea of the breakdown of air. It's going to be important. Okay, you need, I don't know what it is, about 30,000 volts per meter or something will break down air or something like that. Okay, this is huge electric field. It's not as big as the electron held to the proton in a hydrogen atom. That's even a bigger electric field. But this is a big electric field. Okay? And now, where is this coming about? The H plus and the OH minus at the surface have a different tendency to poke into the hydrophobic medium. They're never going to be the same. As soon as I separate charge, you learn in physics, this is going to bounce back and forth between physics, chemistry, and biology before we finish. You learn you have an electric field, and now we've measured it, and it's huge. And that's part what's going on. Let me go back to what the difference is of the interface. At the interface, there is this huge electric field. What else? There is also not possible to have three-dimensional solvation. Bulk, yes. Interface, by definition, is impossible, right? At the most, it's hemisphere, if it's flat. And all this is going to be very important for you to understand the rest of what I'm saying to you about water and why it's so different in droplet form than in bulk. Okay? Now, let's go through this. How much does the interfacial electric field lower the energy to detach the electron off of OH minus? Because I told you the electron comes off. It comes off because there are acceptors. But it comes off by itself, too. We can actually measure a current, which we have. So let's look at this. Baseline, no field at 25 degrees centigrade, that's room temperature. Okay? Room temperature where I live. Redox potential is this, so that the detachment energy, oh, come back. Let's see if I can make this come back. Okay. Is on the order of, it's costing you energy, okay? 2.3 electron volts. Now, you go through this whole process of, you can read this, I don't want to read it to you, okay? And you find out, when you work it all through, that you've shifted by at least 1 eV with this electric field. And so your electron can easily start to come off. And particularly when you get fluctuations, now it'll come off. And the electric field may even be larger than what I just said. So yes, really so, this is what's happening. Now, as soon as you have electrons that can move like that, you're going to have redox chemistry. Reduction oxidation chemistry. Okay. Now, I want to tell you what's causing all this. People first thought, there are many ideas. People first thought, oh, what I'm telling you, I'm going to show you is evaporation and concentration at the surface. Sure enough, certain things do concentrate at the surface, that's true too. But it isn't evaporation, that takes time, and we can show you this happens faster than evaporation. It's something else, it's this electric field. And I want to give you early evidence that curvature of the droplet is important. Here are 2 people in my lab. This person now has gone back to Korea, to South Korea. He's on the faculty there. This person comes from Isfahan in Iran, okay? Which, because he's worked with me, has caused me much trouble. He's a great guy. And he's trying now very hard to get out of Iran for good reasons, okay? As you understand. And this shows a figure. This is a schematic illustration of the experimental setup. Bright field and fluorescent images of microdroplets with radii. And you look at this now. B, bulk water. C is 40 microns. P is 15 microns. E is 8 microns. And we're seeing this getting increasingly brighter this way. And it's taking this material here and it's turning it into something which is fluorescence where we can see it. And so we really have seen again, the same thing I've shown you before, it's increasing very much with small size. And you might say, I know the answer. It's really just a matter of surface area to volume. That's what I first thought. And it's not true, as I'm about to show you. Okay? And I want to actually show you this so I can. Here is the figure again. All this is recently published. This is published within the last year. So there's a reason if you haven't seen this, you know why. And this is showing you that this is a time-lapse fluorescence imaging and reaction kinetic analysis of generation of the hydrogen peroxide in water, microdroplets. This is B. A is, that was what that was. Fluorescence images of the microdroplets. Okay. Other things that are shown here. B is the H2O2 concentration generated by the microdroplets with radii and 3 different radii. What you see is when you start to plot it, that pretty soon you'll find that it goes with 1 over R. 1 over R. 1 over the radius is the rate at which it's going at. Whereas it's not going at the rate of just the area. So I want to now give you a simple explanation for this. And I'm sorry, this talk's going to bounce back and forth, as I told you, between physics and chemistry. There's only one science. Okay. When a water droplet containing electrolyte is surrounded by a hydrophobic medium like air, oil, or vacuum, ions such as hydronium, hydroxide, and other mobile ions redistribute themselves at the interface, leading to the accumulation of net charge or charge imbalance near the surface. So let's assume that the droplet acquires a surface charge, let's call it Q, corresponding to a surface charge density of sigma. That's going to be the charge density, right? Then the electric field is just the, outside the surface is just sigma divided by something called the vacuum permittivity. Fine. Or, looking at this another way, it's the total charge, Q, divided by the surface area. That's 4 pi r squared. R's the radius. We understand how the surface area of the sphere. Okay, fine. That's the electric field. What else? Let's imagine you have a capacitor. You want to see capacitors. Capacitors are flat. They have positive and negative all lined up. We begin by considering a sphere of uniformly distributed dipoles having an infinite radius r, that is flat, just imagine infinite extent. And I'm telling you, above and below r, that's infinity, radius of the sphere, stretch it out, gets 0, no electric field. You don't see an electric field outside a capacitor. You see it inside, plus and minus, but you don't see it outside. There's no electric field. Now, what happens when you bend the flat sheet? You pick up an electric field, and I'm starting to show you. The electrostatic potential psi naught at the surface, not the charge, tends to be approximately constant for droplets in equilibrium with an external environment. The surface charge adjusts with size to maintain this potential. Okay? So here it is. You can read this. That's why sometimes these things are worth studying as opposed to giving you a lecture, but you really want to study it. So look, psi naught is Q over 4 pi epsilon naught r. Okay, and Q, okay, is this thing. I'm just solving for Q, this formula. Fine. Where it is recalled that this negative gradient of the electric potential gives the electric field. Substituting it, taking the derivative, we see that it is really proportional to the electric field to psi naught over r. Psi naught's a constant over r. That's our radial dependence that I'm telling you about. Let's prove it experimentally. Enough of this theory. Okay, fine. Let's now see if this is really so. So here are now more people in my lab who built this device. And what do we have? We're just going to squirt water droplets out into a mass spectrometer. Certainly, I want to make sure everybody understands. Mass spectrometer measures the mass to charge ratio of ions. So not good for neutrals, good for ions, positive and negative. And we're going to look at this, and we're going to send this into the mass spectrometer. We're going to look at what happens. And here we go. Droplet on demand spectrometry. This one works, I think. Just using video, if I can play it. Come on, you don't play. Okay. This is 20 microns. And I can send them one at a time. So this is droplet on demand, you see. Here's 40 microns. You see it getting larger? Here's 60. It's still larger. Okay. At this point, you may find this boring, but you'll understand me when I tell you we can now measure it as a function of the droplet radius. And I'm showing you that. Good. What do we see? We need to look at the mass peak at m over z equal to 36. That's called the water dimer cation. Its structure is thought to be OH-H3O+, okay, which has a lower energy than actually H2O dimer plus. So even if you take an electron off of H2O, it'll form this OH-H3O+. Okay? We're going to use this mass at 36 as a measure of how reactive is the water droplet. And here's what we find. I am looking at you. Here's the intensity of 36. Here I am, and I'm looking at the droplets versus droplet surface area. If it were linear with area, if it just scaled with area, it would look like this. It doesn't. It's curved over, right? What happens if I instead went over the radius? Okay, this is the I-36 per unit area now. Plotted went over the radius. Almost a straight line. Wow. That's great. It really is showing you what I'm saying. Electric field goes up. You want smaller droplets to make it work. Can you just go on and on? No, at some point the what's called double layer, electric double layer, plus and minus, overlap each other. So it has to shut off. But before then, you can go down to nanometers, nanometer-sized droplets. Still works. Okay. So is this the end of the story? No. Now, hopefully, this will make sense to you, because more hydroxyl radicals are generated as the radius of the water droplet shrinks. Keep getting more OH, right? There's a competition between the reaction of the OH with something and the OH recombining with itself. And guess what? Quadratic beats linear every time. So at some point, you're going to shut down the OH, right? It's not going to just go on getting more and more reactive as you make the droplets smaller and smaller, I think. So the rate of product production becomes optimal for a specific water droplet size. That's my claim. Is it true? Let's look at something. Here's a molecule called melatonin, okay? And you see what it is. Melatonin actually forms ions. Here it is with the sodium ion at 255. Here it is by itself at 233. And here it is with OH at 250. Okay, what's happening? And now let's look at it. Let's look at the intensity at the thing at 250, where it's picked up something. And I'm showing you how it scales. It doesn't scale with what? This is looking at just the electric field of the product. And it doesn't go up linearly. It goes up like 1 over R, the forming stuff. But now look at the product. The yield of the oxidation product, okay, is a function of inverse droplet radius. Let's look at it. It reaches a maximum. Where? At about, I'll call it 0.1. So on the order of about 10 microns is best. 10 micron droplets give you the highest rate. And it starts going down after that, not because you aren't making OH. You are making more OH, but it's finding, OH is finding itself first and stopping reaction. Okay? Now, again, this is very, I think, very interesting in showing you something about droplets. What about, is this general? Yes, I claim. There's something called methylviologen, also known as paraquat. Okay? And it's a well-studied molecule used a lot in electrochemistry. It's called MV++. It's a dichionic iridium species. Okay? Because of its strong positive charge, it is highly soluble in water and undergoes well-defined stepwise 1-electron reductions. MV++ accepts 1 electron to form MV+, the methylviologen radical cation. Let's look at it. There's the mass spectrum showing the reduction product of methylviologen in single aqueous microdroplets. You understand, I really can look at a single droplet. You see why. Have droplet on demand, like inkjet printing. Okay? And here I'm showing you it. Here's MV++. Here is the stuff that is, remember, it is mass over charge. This gets divided by 2, charge of 2. That's why it's appearing here. These are just MV+ type things. And you see how what they are like. We know what they are. Okay, great. And so the total product intensity is calculated by the summed intensities of the M over Z values for 171, 185, and 186. Okay? Let's look at it. Does it go with area? No. We've seen that before. Okay? And you understand what I'm telling you. It's not surface area. Does it go with curvature? Yes. Look, it's almost linear. Not quite, almost linear. And what else? Look at the product. The product reaches a maximum. This maximum is at 0.2, and so something, so it looks like it's 5 microns. Okay, this is the best. Well, we're really seeing something here. And okay, this sounds fine. We understand now that curvature matters. It's changing electric fields, helping to drive the process. You learn in chemistry after a while that it's electrons that move to make a big difference, and then move in response to an electric field. And I'm giving you an electric field from this process. Let's go on and show some more examples. First thing I thought I would share with you, sorry, this is not published yet, is that we can make boron nitride quantum dots. After coming here and realizing your interest potentially in boron nitride quantum dots, I thought I'd show you that we can actually, by spraying and combining things, okay, we could take borane ammonia complex and we use them as precursors. We spray them. All we do is spray them, and we get these quantum dots. That's how it works, and it's worked because of this chemistry, because of the fact we have H atoms and OH radicals that can go on and react and make them come together. And we really see that happen, and we're able to make milligrams at the moment per hour, and about 2 nanometers in size. And I want very much to see if I can learn how to scale this up. I don't know how to yet. I'll show you another example. This one, I think, the boron nitride, I can see potentially how it can be used for weapons. This is much harder to imagine how it's going to be used for weapons. I want to tell you about plant flower. I'm talking about plants that give off flowers, okay? Some of you may know that, or have noticed, that plants are flowering earlier in the year as a function of years than they did before. For example, the height of the cherry blossom season in Washington, D.C. occurs earlier in the year. That's been going on. I have data I can show you about this. The question is why? Well, people say, oh, it must be global warming. Well, you take the plant and you put it in a greenhouse and you can make the temperature change of global warming. There is a change in temperature, some. It doesn't affect the flowering. Not global warming that way at all. Is it sunlight? No, global warming doesn't affect sunlight. Really, you get as much warming. That's not obvious at all. What does it do to? Well, it is global warming, but in a very subtle way. You get much more moisture in the air if you increase the temperature of the air. And the result is you form dewdrops earlier in the year on plant leaves. And dewdrops, now you're beginning to understand, dewdrops are going to make OH, and OH and H. And what are they going to do? They're going to go to things like arginine, and they're going to make NO, nitric oxide. NO is a signaling molecule, very important. Men know this particularly, okay? And anyways, to continue about this, it happens in everybody's body. NO is being used. It's happening in plants too. And you run a bunch of enzymatic cascades. Notice, published in 2026, we really find that spraying can change when, with water or mist, when you get the growth of the plant. That's news, okay? And we see with, I think that there must be applications of this. We'll move on. I'm going to give you another unpublished result. Sorry. Lots of things are happening here, and who are the people? Some of you, let's see if I can do this. Some of you will recognize this molecule, not others will not. This is called squalene. This is an oil that you first found in whales. Okay, this is squalene, and squalene is actually turned into steroids through a process that goes through this epoxide and then onwards to fold up to form steroids. People know this happens. There's a whole industry based on this, how you make cortisone and so on, vitamin K, many things, right? And they all require enzymes, so it appears, but they don't. I want to show you you can do this without enzymes. How? By just spraying water droplets, or shaking water droplets with the material in a medium. And we now capture the stuff, we see all the intermediates, and don't have more to show you, but I would. Okay, I'm going to now leave this. We see like 20 different steroids that are produced this way. Quite amazing. And so I want to tell you the whole type of chemistry that can be done now with water droplets. And it's what you call green chemistry because it's being done at room temperature. It's not being done with addition of any metal catalyst. Doesn't have to be anyways. And what else about it? No electric field's being applied. Electric field comes from itself, with the droplet, the interface. No radiation is being used. No radiation can help it. Now I need help to try to show you a video, because I want to go on and clearer so what's happening. So we're going to now move here. Try to make this go. This go.
My entire life.
Yeah, definitely here. I'm thinking it's not here. This is what I want to show you.
The North Carolina coast of the United States is lighted by explosive sonic booms, the locals call Seneca guns. Sometimes they sound like fireworks. The strongest can make the earth
Turn the computer
rumble.
down.
Claudette and my cousin had just moved to their new home in a peaceful seaside town near Cape Fear. They were looking forward to enjoying their quiet neighborhood until
I was sitting at my desk in my office, working away at the computer, and I felt this large room. So loud, like the windows shook.
this wasn't an isolated event. Several times a year, earth-shattering booms startled Cape Fear residents. In April 2012, Paul Laser set out to record the booms that had been shaking his parents' house for years. After weeks of patient waiting, Paul Laser had finally recorded this mysterious phenomenon for the first time.
It's real.
That went to the fireside. It didn't shake the house or rattle the windows, but it definitely, it was loud enough that I knew exactly what was going on when it happened.
People isolate the sound because the sonic pulse of what causes the Seneca guns. Scientists have discovered earthquakes, thunderstorms, and interplanetary jets. If there is no obvious scientific explanation, could there be one that defies rational understanding? Like many Cape Fear residents, Ivy Bird is unsettled by the terrifying booms.
Sometimes at night, if I feel the booms, I'll look outside, and I'll occasionally see orange glowing balls out over the sea, and I don't know what it is. They just stay there. They're in a little pack, but it's not a plane or anything because it doesn't blink. It's just an orange glowing ball.
Ivy says she only sees these lights when Seneca guns occur.
It does feel like the booms are coming from the same direction as the orange balls.
If they are related, what could they be?
Okay. Stop them.
Staff this frozen lake in the right place, you can light it on fire. But it's not the water that's flammable, it's actually what's bubbling up from the lake floor. These aren't your average lakes. They're called thermokarst lakes, and they're filled with highly flammable methane gas. During the summer, the gas bubbles to the surface and enters the atmosphere. But in the winter, the bubbles get trapped under the ice. So when you stab the frozen surface, it releases pockets of the gas that you can then light up. It may look like a funny party trick, but there's more to this effect than meets the eye. Methane isn't just highly flammable, it's also a potent greenhouse gas. 25 times more efficient at trapping heat than carbon dioxide.
Okay, enough of that. So let's now try to summarize something. We get the idea finally that there are, what should we say, bubbles of flammable gas. It's not just simply methane. We've now learned enough that from the droplets, etc., we also are going to pick up H atoms, which are going to recombine and form H2. We got really a mixture of H2 and methane. And H2 plus methane, right conditions, going to explode. Okay? That's the orange balls up there you were seeing. This question still is, what sets them off? Why do they burst the flame? This goes back to what people call will-o'-the-wisps. People see around swamps, cemeteries, etc. Blue lights flicker. They think, oh, it must be formaldehyde in terms of analyzing it, but what's causing it to burn? Okay, I'm going to explain that to you. And this, I think, is news and it's relevant to some various things. So, discuss it. I'm making a mess.
No, you're good. Just gonna see it a little closer.
Oh, thank you. Okay, so this is work done by a person who was in my laboratory by the name of Shiv Banerjee, who's back now in India on the faculty there at Isar Tirupati. And he reports that when he sprayed water, he was finding various ions being formed, like N2+, O2+, and NO, okay, many other things, CO2+. And I will present arguments that the observations are correct, but his idea that he thinks it all comes just from a corona surrounding a single water droplet, that isn't correct, okay, in my opinion. And I'll show you a different interpretation of what's going on. And again, one which is news and very recent. First, I want to show you the reproduction. Here's my group who published this 2024, okay, in which we repeated the experiment of Banerjee and coworkers and found the above. You see all the ions? So come on back. Okay. And we did this from deionized water, with no voltage being applied, using air as the nebulizing gas. I want to make it clear to you, because there's been all types of confusion in the literature. Some people say, oh, these radicals, they're coming from discharges that you've made. Well, I can show you that dewdrops on plants don't make discharges, they just form, okay, or condense out. People say, oh, it's all coming from ozone. Well, yes, there's some ozone, but no. We've done scrupulous experiments, not from ozone. Other people say, if you're confused, it's the ammonium ion. You're not looking at water at all, water nitrocat ion. That's also unfortunately wrong. But enough of that. Anderson, let's not dwell with what's wrong. Let's talk about what's right. Okay. Here is a picture of a person who is a great physicist and a horrible human being in my opinion. His name is Philip Lenard. And in 1905, he received the Nobel Prize in Physics. He discovered that the energy, or the velocity of the electrons when you shine light on a metal, okay, depends only on the frequency of the light, not on the intensity. We call this the photoelectric effect. And many of us have learned to attribute this not to Lenard, but to someone else. Who? Einstein. Right? It's Einstein first worked this out. But Lenard got the Nobel Prize in Physics in 1905. What's worse is that Lenard was a nationalist and an active proponent of Nazi ideology. He labeled the work of Einstein as Jewish physics, and he contributed to forcing Einstein out of Germany to the benefit of the rest of the world, in my opinion. Okay, well, what else did Lenard do? Lenard went and he studied a waterfall. When? 1892. And he found that the little droplets were negatively charged and the big droplets were positively charged. And that's called the Lenard effect, and it's true. It's so. And I want to show you that that's so. This is going to be important to understanding things. So again, we're going to go to a video. First, I want to show you the setup, because seeing is believing. Here's a high-speed camera, okay? I have here a syringe pump, just a syringe, you pump out water, and I'm going to have a little bit of compressed air or some gas to help the droplets come out, okay? This is in the lab. This is lab air, And they're going between two copper plates. I can turn the voltage off, or I can turn it on leftly. This is negative here, positive here, or you can reverse it, whatever. Set up. Now, let me show you if I can what's going to happen. I'm going to claim to you that there's a difference in the Fermi levels of little droplets and big droplets, and when the droplets start to come off, you're going to have electrons that jump onto the little droplets. Electrons move much more rapidly than protons, etc. And you're going to have, from neutral water, you're going to form charged droplets. You're going to see, and again, people don't realize this generally, that all droplets are charged. I'm going to show you that. I hope I will. Let's try. This is another video. And you see the setup. Okay? Up. Positive on this side, negative on this side, which you can turn on. Let's do it. Okay, it's running. And you have to be patient. High speed, so we can show this in slow speed. Look what we're seeing. We're seeing nothing. We see the droplet coming off, but it's moving negative and positive. See it? No neutral comes out. None. And it goes on. And okay, after you see it a little while, it's boring. But you get the sense of what I'm telling you. Okay? Fine. Let's go on. We use something called a Kelvin probe force microscope, and we can actually determine the charges on the droplets. And sure enough, the negative ones are smaller. This is the droplet diameter than the bigger positive ones, and we get a sense of what they're like. And we can actually measure the amount of charge. Does it get the amount of charge out here? We can actually see that it carries charged little droplets, and we work it out. You can see how many positive charges there are on one, how many negatives there are on another. Fine. What else? Please look at this. If you bring negative and positive close to each other, on the order of about 1 nanometer or less, you get an electric field again. And how big the electric field? This one goes up to about 10 to the 9th volts per meter. That's what I was telling you. Okay, that's amazing. That's a big field. That field is big enough to break down air. And that means that you'll get an electrical discharge. And I'm going to call that electrical discharge micro lightning. That's a name I made up for it. Okay? And I want to convince you that micro lightning is real. And first of all, what if we just spray water droplets? Again, no applied external electric field, no radiation, and we surround it with different gases. Here, I can't read them. I'm sticking my head in. Here's a gas. What is this one? This one has looks like 3 chlorines or 4. Oh no, this is carbon tetrachloride. Here's carbon tetrachloride, and we see ions. We put in benzene, C6H6, and we see C6H6 plus, and we've actually plotted this, the ionization potential, which falls off. And so the conclusion we reach is the electric field is greater than 11 eV in magnitude, which is enough to dissociate, excite, and ionize most molecules. Little lightning, micro lightning is happening. Okay? And now, let me try to show this to you. It would really help if I could kill the lights, but I can't. Okay, here, please look carefully. We're going to suspend with acoustic waves, with sound waves. We're holding a droplet. It's evaporating. Little droplets are coming off. It starts out neutral, and it's getting positive. And if you're patient, please look. Did you see it? That was lightning, micro lightning. Okay? Let me show you some more. I'm going to show more video. Incidentally, it took us easily over a month to learn how to make these videos. This is, you don't see this by eye. You've got to work hard. Okay? But come on, where is it? There we go. Let's make it go. Here, holding it. You see the little droplets coming off? That's what I'm telling you. It does that. And then here we'll do it with applying a voltage. Come on. Here it is. And you'll see, we because we turn on the voltage, all the little droplets will move to the right, where there is the positive electrode, because they're negatively charged. You see them migrate. Okay. As it goes on. So it is the Leonard effect again. And you believe this. Now let me try to show you some more. Here I'm going to show you through a blue filter. I hope I can take the video. There. Did you see the blue flash? Did that again? Here's a photomultiplier seeing it. There really is a micro lightning happening with droplets. And again, I can show you more of the data. Let's go on and visually, because seeing's believing. I'm going to drop a droplet on a surface and have it splash. I do this first with dim lighting. Okay? Let's see if we can make this go with dim lighting. Here we go. And it drops, and it splashes, and so what? Right? And by eye, I can see nothing. Now, let's do it with the lights off and get everything done well that way. Please watch. See it? Little tiny white flashes there that we see, that's the micro lightning. So I hope at this point you believe me about micro lightning, because I'm telling you it's the micro lightning which is setting off the explosive mixture. We have now an explanation for how you can get will-o'-the-wisps and the guns of Seneca that they hear in Cape Fear. Okay, and I can show you more of this. Again, you see the setup: water pump and micro bubble generator. Now we're going to bubble stuff. I don't know that I've made it clear to you. I hope I'm okay with time. Got about time. 10 minutes. Got it. Okay, I'm sorry. I'm running over, I think. But I'll get done pretty soon. But I think you're going to get the point soon with this. Wow. What else can I say about this? Wow. I can tell you that this stuff really happens. And we can, is this going to be a video? No? Okay. This is ignition induced by interbubble discharging. Oh yeah, here's a video. This is bubbles. Please watch. This is timing. Look, see the timing in microseconds? Look, see the white? Okay, it's there. It's really so. This is important. This is really what's going on in water with bubbling. So water, which looks like it's so inert, now I'm showing you micro lightning. And I'm showing you I can set things off. More of this. Let me now bubble hydrogen through water. This is going to be bubbling hydrogen through water with the pump on and the pump off. With the pump on, I see light. I record light. Turn the pump off. Okay, gone. And you know, I'm burning the hydrogen from these micro lightning. And I can go on and show you more chemistry. I haven't done that. And I'm not going to explain to you some of the worries here about methane coming off and how there can be a feedback, and that can lead to very dire consequences of runaway warming of the Earth's atmosphere because of all the methane that's trapped in frozen ice. I want to move to another topic that's very much related. Okay, in the 1950s, a Nobel Prize-winning chemist, Harold Urey, noted that the most atmospheres in the solar system are dominated by nitrogen and methane. And Urey reasoned that early Earth also had this type of atmosphere, and he proposed this earlier atmosphere could be very efficient at making organic compounds. Let me remind you, to get life, you need carbon-nitrogen bonds. Carbon-nitrogen bonds are what you find in what? Chlorophyll, in RNA, DNA, it's what you find in amino acids and proteins. But where's the carbon-nitrogen going to come from? You don't have it to start with in terms of the atmosphere. And so he built this device, which I'm showing you here, in which he used the spark plugs from a combustion engine of an automobile of its time. Today we're switching to electric. It's not the same. But talking about a gasoline engine, okay? And what else? He filled it with these different gases, and his student, Miller, did these experiments, and they analyzed it, and they found all types of organic compounds. Here I am showing you his original apparatus. This now exists in Urey Hall at the University of California, San Diego in La Jolla. Okay? And here you can see the setup, and I'm telling you, it's very simple to do. And there have been objections to the Miller-Urey hypothesis. This is what I learned first when I was going to high school. People said, oh, it's really due to lightning in the sky that makes building blocks of life. And then people said, wait a moment, lightning's intermittent and unpredictable. And whatever compounds are made in the sky's big, goes everywhere. You need to accumulate them and polymerize them. It's not enough to make a building block. You've got to make the building blocks come together. And so people have nevertheless continued to study this, but the objections were not overcome of what I'm telling you. How do you concentrate this stuff? And here it is, my student, Yifan Meng, now again returned to China. Anyways, he made all these compounds. By what? By what you see. Putting in these gases, none of them having carbon-nitrogen bonds, and just using water spray. Micro lightning. And you get this chemistry. Look at the chemistry you get. You get things like urea and uracil and so on. And I want to show you proof about that. You can even make hydrogen cyanide this way from this, which he showed. And so we propose that this is a new mechanism for the prebiotic synthesis of molecules that constitute the building blocks of life. And why this is so interesting is that you get water sprays over Earth everywhere, particularly on rocks. Rocks have cracks and crevices. You get then wet dry cycles which can polymerize things. And so this can really lead to the beginning of how you can start to make things. And now I've gone on probably long enough. So water droplet sprays are common in nature. Reaction products are easily concentrated and they can undergo cycles of wet dry polymerization. And so I've taken you on this journey, and it looks like a whole new type of chemistry can be done with water droplets. And I hope you enjoyed this. Appreciate it.
Do we have time for questions?
Yeah. Copy of this by just using my email address and writing me. I'll send you a copy of this lecture. Question?
In one of your plots, you showed NO2 plus ions being formed. Have you tried doing any nitrations using the microdroplets?
Yes. All types of chemistry can be done. We are actually able to make ammonia and make nitrates and nitrites by this process, and we published that. Again, all within the last year or two. And so, again, I'm excited about this. If one could learn how to scale this, and Pat's been showing me some things that are pretty exciting about scaling, okay, it will change the world. Because you do want to get away from the Haber-Bosch process. It's so unfriendly in terms of what it requires. For example, something like a few percent of the carbon dioxide that you and I are now breathing come from the Haber-Bosch process.
Can you duplicate this chemistry by cavitation of liquid water?
I think you can, yes. So that's, I don't think I'm bursting bubbles that way, but yes, you can. That can go on too. That's very important.
Do solvating electrons come into play here?
I think I haven't been able to prove that yet, but I expect that to be true.
So work's being done with liquid ammonia?
I haven't. There's so much here that can be tried further. And please, nobody owns water droplets. Everybody can use it. Way in the back.
So I've seen some techniques for internal combustion engines where they atomize water and mix it with fuel and air, and it has certain benefits. I don't think I've seen this as a potential explanation for those benefits. Is that something that comes into play?
Let's let's see if I understand your question. We are indeed, by atomizing, making water droplets, right? That works. But you can also do gas bubbles. You can use a stone that's porous and force a gas through it and make little bubbles, same effect.
Okay.
It's all interface chemistry, and I hope I've explained to you how the interface is so reactive. It's just starting to be exploited. All types of chemicals can be made this way, I believe. Now, the real advantage will come about from scaling. It's one thing, okay, I publish papers, that's good for the academic world, that's fine. What really matters is, can we make it on an industrial scale? That hasn't been demonstrated yet, but I'm hoping it will be. Okay.
So from
Get the microphone.
from a more fundamental point of view, so it looks like that what you need for that is not just water, but you need hydrogen bonding. Have you done any calculations of if you use different molecules, for example, ammonia, or if you increase the strength of HF?
Okay.
How that would change things?
Let me tell you, I've tried this with some other solvents, like acetonitrile or like methanol. Doesn't work. I need the water itself that likes to form H plus and OH minus, whereas methanol doesn't like to ionize as much.
Yeah, that's my point. By HF, for example, hydrogen.
But that will help you. You can add that and make things go. You can also change pH. I didn't go through that, which is another way of making this go. So this is so many possibilities here. But I do want to leave you with the thought that it's real. Okay.
We have a question in the chat.
Oh, please.
Similar to microdroplets, do you think nanobubbles also might show reactivity?
Absolutely, we've done that. Very much. And I'm trying to tell you, the nanobubbles are better than microbubbles for the reasons I've mentioned to you about curvature. And we've used just air that's nanobubbled through water, and we make nitrate and nitrite from it, which is our fertilizers. And again, we don't have to do anything more. If it can be scaled, we win. I'm very interested, personal idea, okay? I'm very interested in whether or not we can use the ocean to remove certain greenhouse gases from the atmosphere by bubbling through the ocean. I think it might work, but we have to, again, learn how to do that economically with scale.
And there's a second part of this question. How do you think the reverse interfaces with nanobubbles might affect reactivity?
The same way. Not exactly the same way, but close to it. They both work. We've done that. We've actually used nanobubbles. And that's what I was trying to show you. That work at the end about lighting things up with bubbles. Yes.
So I'm just trying to fully understand this interface, trying to envision it in my head. So you see so much hydrogen peroxide throughout your droplets, but you see like capacitor layer. So I'm just wondering, like, how is all of that working? Because the peroxide would create that.
Okay, at the surface, at the surface, hopefully you understand I'm forming OH, the hydroxyl. The OHs are wandering around. If they find each other, you get what's called radical recombination. That's how you get hydrogen peroxide, and we have lots of evidence showing this is so.
And you think that the OH is also creating that capacitor layer
Also,
the interface?
I think the capacitor layer comes about because of ions that have a different ability, positive and negative, of going into the hydrophobic medium, whatever is touching the water at the interface. And I think I need an electric field that helps to make it small droplets rather than large droplets. Flat doesn't work. So flat air, like a swimming pool, no big effect. Little droplets or little bubbles, big effect.
Okay. And for your mass spectrometry, what ionization method are you using? Are you using electrospray? Because
I have used nebula I want to make sure you understand. I've just used nebulization, in which I force the droplets through a capillary to come out as the water to come out as droplets and dissolve things in the water.
Okay.
And we've done many, many other things. For example, just so you realize, I can take silver nitrate that dissolves in the water. I spray it and I get silver film because electrons, which you can see where they're coming from, will jump and reduce the silver. I've done that with many things. Do that with gold as well. Take a gold chloride and no, this is real. And I'm hoping now I can recover gold from waste streams this way. Or somebody can. I'm not going to personally do this. You understand? Oh, question?
Yeah, you were talking earlier about maybe being able to apply this to like the ocean somehow. Do you have a feel for how you think that salt concentrations might either help or hinder this charging process?
I think it's really the process is primarily coming from water. So there's plenty of water, and I don't think it's going to affect the small concentrations. We've done other things, again, collaborating with other people. For example, we find that the salt water, we can actually turn it into bleach. HOCl.
Do you know of anyone who is doing the work to see if a more basic solution with more hydroxide radicals would increase reactivity?
We've played with that. There are a number of people now working in this area. Honestly, this is an active new area in chemistry, this droplet microchemistry, and Pat can tell you more too. Thank you all very much.
We just want to present you with this award with gratitude for your contribution as a distinguished lecturer. Thank you for your commitment to advancing innovation and the Navy Tech Connect mission to connect ideas, technologies, and people in support of the work.
Thank you. Thank you.